Good evening. I work in a team that develops hydraulic simulation software for roof drainage systems. And to automate the building process, we developed a classic machine learning solution based on supervised learning and neural networks. However, by the end of last summer, we had to realize that we won't be able to improve our solution any further, meaning even a larger data set, more compute power, better algorithms won't be of any substantial help anymore. But nonetheless, our users, our experts, often find a solution to their planning problems, essentially by playing around. And this kind of playing around is a key ingredient of reinforcement learning. Reinforcement learning is a form of machine learning that does not depend on a training data set, but instead uses the interaction with an environment. So we will dive into the topic in a playful fashion, illustrating the way the algorithms work by the way a child might learn a new game. In the second part of the talk, we will then apply reinforcement learning to our hydraulics problem and see that using this approach, we were able to reduce our fail rate by more than 70%, way beyond our expectations. So let's get started. Children are true masters at learning new stuff. So whenever you give a child a new game, you press a new game in their hands, they immediately start pressing some buttons and seeing what happens. It's interesting to see that you don't have to explain to a child how the game works. It's part of the thrill to figure it out. And also, once they've mastered the game, they usually can't tell you why they took this or that move. They essentially play in an intuitive fashion. And we will rediscover these two properties also in the output of our reinforcement learning algorithms. As an illustrating example, I would like to use a simple game called Snakes. I chose it because it's very easy to understand, but nonetheless, it takes quite a bit of a strategy to play it well. So let's take a look. We play the game by using the arrows, moving the snake around. And for each step we take, we get a reward, which you see on the upper left-hand side, like this one here. So whenever we eat one of these square things, we call them fruits, then we get a reward of 100 points, and otherwise just -1. The game ends when either the snake drops off the board or when the snake collides with its own tail. So initially, the game is very easy to play. We just we just eat greedily the next fruit available. But the longer we play, the longer the tail gets and the more difficult it gets. Thus, suddenly, after a while, making a bad move now can easily result in a losing position down the road. For example, now I made a mistake and I'm now in a dead end. I still can move, but clearly the end is near. So to win this game, we need a strategy which is able to look quite a few steps into the future. So let's see how a child might try to learn this game. Initially, the child has no idea about the game, no clue. So it will just start by pressing some random buttons, which we also call actions. And for each action taken, we get from the game engine a feedback in the form of a new game state. And this new game state then is the input for the child on which it bases its decision which action to take next. And also, for each step taken, we get a reward, either a positive or a negative one, telling us how good our last action was. And of course, our goal is to maximize the sum of rewards. So as the child keeps on pressing some random buttons, at some point it will make a fantastic move. It will have a lucky strike, meaning it will take an action which results in a high positive reward. And learning from this positive experience now means that the child will try to take the same action again in a similar game state. Of course, the opposite can happen as well. So the child will take an action resulting in a high negative reward, and learning from this bad experience means that from now on the child will try to avoid taking this action in a similar game state. And as the child keeps on learning like this, its gaming strategy is improving. And this gaming strategy, or the thing that the child is learning, we also call it a policy. And we view the policy as being separate from the learner. So it's the task of the policy to be the decision maker. So it's a policy who decides which action to take next based on our current game state. Such a policy can be very simple, like a random policy, or it can be a very intricate one, like that one that always reaches the maximum number of points on average. And if it is now the task of the policy to be the decision maker, it's the task of the learner to improve the policy once the game is over. And like this, after each game, the learner improves the policy and we get a better one. And then we play again, and once more we get a better one. So reinforcement learning algorithms now try to learn by mimicking this behavior of the learner. And the key idea here is to design an algorithm which is able, based on an existing policy, to improve it just by the interaction with the gaming engine. Now, this is an incredibly bold statement because it means we can start with a random policy, we take a game about which we know nothing, we just start the algorithms and let them run. After a while, we just wait and see, and after a while, we will end up with a new gaming strategy which plays the game rather well, without providing any additional information to the algorithms. So it sounds, it's almost a bit like magic. So let's see how this magic works. So we fire up our game engine and we get an initial game state. Since we have no idea about the game yet, we start with an initial random policy. That means that's a policy that chooses a random action. And to keep things simple, let's assume that each action has about the same probability, which we represent with some background on each of the actions. So we now let the policy choose which action to take next. It chooses to go left, we get a reward of -1 since the snake just moved, and we get a new game state. And now we're ready to move on to the next. However, our goal is, after the game is over, to improve our policy. And in order to do that, we must be able to remember which steps we've taken. Thus, we record each step, meaning we record the state, we record the action we took, and the reward we got. And like this, we keep on going. So we move on to the next state, we let the policy choose. This time we eat the fruit, we get a high reward, which we record as well. And we move on. And now in this last step, the policy chose to go up, which means we dropped off the board, we died, and we got a high negative reward. Therefore, the game is over now. And since the game is over, it's now time to do the policy update. And we do this stepwise, starting with the last step. So clearly, the last step was a bad move, because after all, we died, we dropped off the board, we got a high negative reward. So learning from this bad experience means that from now on, we will try to avoid taking this up action in this game state. Or in other words, we will reduce the probability of the up action. And we represent this with some red background. Now, this is actually a crucial step, so let me repeat this. We learn by changing the probability of the action we took in the current game state that we are in. And now we move on to the previous step. Again, this time we took the left action, and now we want to update the probability of the left action. But since our goal is to get, in the end, a policy which is able to look into the future, we now must take not only our current step into account, but also all steps between now and the end of the game. And we do this by taking the sum of rewards between all steps between now and the end of the game. So we just calculate the sum. 100 minus 50 yielding 50, which we consider to be a good value, and therefore we increase our preference for the left action. And we move on. So now we calculate again this sum of future rewards, and we get this time 49, which we also consider to be a good value, and therefore increase our preference. So now the policy update is over, and we move on to the next game. This time we use the policy that we've learned, that we already improved. And to keep things simple, we start again in the same game state as we did in the first game. So we already know something about the left action. We also already consider this to be a good action. And therefore, we let the policy choose again, and it chooses to go left. And we keep on going. Now, policy chooses to go left again. And here in this state, for example, we already know something about the up action, namely that going up was a bad move. And therefore, going up has a reduced probability. So we let the policy choose, it chooses to go down, we eat the fruit, and we keep on going. And finally, the policy will hopefully make a mistake. We jump off the board by going to the left-hand side, so the game is over again. Now we do again our policy update. So we start again with the last action, the last step we took, and we again calculate the sum of future rewards. This time it's just one summon, so it's just a -50, which is a bad value, and therefore we decrease. We move on, keep on calculating the sum of rewards. And for example, now in this state, or in this step, we took the down action. Although we already know something about the up action, we only update our preference for the action we actually took in the current game. So we don't care about the up action at all. We only care about the down action, which yielded a value of 49, which we consider still to be a good value. Now this step is probably the most general step, and that's the actual update we will do, we always do. So if we do it naively, then we now calculate the sum of rewards, yielding 149, which is a fantastic value. We've never seen such a high value before. So in a naive update, we would now change the preference for the left action, overwriting our previous value to something like this. But if we now overwrite our previous value, we forget everything that we've learned so far in all previous games. And of course, we want to incorporate our previous knowledge also together with our new knowledge from our current game. And in order to do that, we take some form of a running average between our previous value and our current one. So we settle for something, some ground in between, some value like this. And we move on. And here it's the same story again, so we get a very high reward and we take some form of a running average. And like this, we keep on playing many, many games. But instead of playing a third game, let's take a step back and see where we are. So we have this notion of a policy. The policy is our decision maker, the guy who decides which action to take next. Thus, we can view the policy as a map from game states to action probabilities. Because as an input, it gets our current game state, and as output, it yields the action probabilities. Thus, we can view it as a map. And such a map we can readily represent using a lookup table, indexed by the game state. Initially, we started with a random policy, meaning we started with a lookup table with random values. Then we started playing games, and after each game played, we updated the values or our preferences for these actions, meaning we updated the values in our lookup table. And like this, we got a whole sequence of these lookup tables or different versions of it. And if you keep on doing this, like for many, many games, like for 10,000, 100,000, or 1,000,000 games, then we will end up in each game state with a nice set of action probabilities. And these action probabilities actually represent the essence of what we've learned. So that's the condensed experience of all these games. And that's what we're actually looking for. So we can now turn this approach into code like this. We start by initializing our lookup table with some random values. And we then start playing games. We enter a loop and we play our first game. We use the lookup table to decide which action to take next. And for each action taken, we then record the step we took. And once the game is over, we enter the policy update phase. Meaning for each step we've taken, we compute the sum of future rewards, and if this value is high, then we increase our preference for the action we took in this step, and only in this step. Or if it's low or negative, then we decrease it. And like this, we keep on going on. And I used an algorithm like this to train a policy for the snake game. So let's take a look how this feels like. So we now let the policy play the game. Note that the snake did not drop off the board, so it has already learned rule number 1. And it's kind of eating the fruits, but not in an over-aggressive fashion. So it's trying to avoid colliding with its own tail. Now it's looking good. So I'm happy it has won. Actually, to be honest, it doesn't win always. It just wins in about 50% of the cases. But in the rest of the cases, it usually gets a rather high reward. So let's see how random policy looks like. So like how a policy looks like with which the algorithm started. Okay, so this one jumped off the board immediately. Let's try again. So it's running around erratically before jumping off the board. Or like a medium well-trained policy looks like this. It's not aggressively jumping off the board anymore, which is good, so it has learned something. But it's not top-notch yet. So this seems to be a fantastic algorithm, and it is, but it is only in theory. The problem with this algorithm is it simply doesn't work in practice. The key problem is that in practice we usually have a very large number of different game states, yielding an incredibly large lookup table, requiring a lot of memory and even more compute time. So this is simply not practical. Even in the case of the snake game, we have about 500,000 to 1 million different game states. And when we enlarge the game, the board size from 6 to 10 or something like that, we get an incredible combinatorial explosion. So I wouldn't be able to train that policy anymore on my laptop. So the key problem is really this lookup table, but we use the lookup table only to represent our policy function. And we know that neural networks are excellent function approximators. So the key idea here is now to use a neural network to approximate this policy function. That means that in our algorithm, now instead of updating the values, we will now have to update the weights in the neural network. And this only has a small impact on our algorithm. So let's first take a look at the neural network side and then move on to the algorithm. So whenever we have a neural network, we must choose a network architecture. But through the network architecture, we directly control the memory requirements of our algorithm. And therefore, we directly address the key problem we had so far with our lookup table. To use the network as a policy function, we must encode our game state as a vector, which we can easily do. And then we take this vector and send it through the network. And as an output, we want to have one value for each action. And these values represent our preference, which could be arbitrarily large or arbitrarily small, whatever. And we then turn these out values into probabilities again using a softmax function. So all we have to do now with our algorithm is kind of find the right weights for this neural network. So let's see how this algorithm now looks like. So instead of initializing the lookup table with random values, we now initialize the network with random values. We then start playing games again, using the network with its current weights. And once the game is over, we update the weights. So let's assume that in our current update step, we took the up action and we have a very high sum of rewards. That means we want to increase the probability of the up action. If we want to increase the probability of the up action, means we want to increase the out value for the up action. And in order to do that, we now must find the right changes for the weights to increase this out value. But since we have a neural network, we can readily compute the gradient. And the gradient exactly yields us the weight changes we need. So therefore, all we have to do is we take our current weights and we add the gradient to it. Of course, sometimes the future reward is very large and we want to increase our out value a lot. And sometimes the future reward is negative and we want to decrease it. So in order to incorporate this part, we simply multiply the future reward with the gradient. So all that remains now is only we somehow have to control the impact of which our current game has on the weights we've learned so far in all the previous games. And in order to control this impact, we use a factor, which we call alpha, the learning rate. So initially, we will have a learning rate of alpha, which is close to 1. So our current game has a strong impact. And the more games we play, the less impact our games have. So we decrease alpha towards 0, so that the last games only have a minor impact on the weight changes. And essentially, that's it. There's a whole family of algorithms that roughly works like this. So this is still kind of a sketch. It's not, you wouldn't want to implement it like this in detail, but it gives the general idea, the intuition. And there's a whole family that works like this, and they are called policy gradient algorithms. And the reason why is because these algorithms, we directly represent this policy function using our neural network. And we update this policy function by gradient computation. So that's where this name derives from. If anyone is interested in the math part behind it, I'll be more than delighted to show it to you afterwards. It's not very complicated, but it has some clever moves in there. So this was kind of the first part of the talk, the part about the reinforcement learning algorithms, and now let's move on to the application side. I work as a consultant for Geberit, which is a sanitary technology company with about 12,000 employees. Geberit produces in particular pipes and stuff to get the rainwater off the roofs, of flat roofs, so-called syphonic roof drainage systems. It is surprisingly difficult to find the right diameters for these pipes. It's actually so difficult that as of today, there's no feasible deterministic algorithm which could calculate these diameters. That's why we have to resort to heuristic algorithms and machine learning to find these diameters. Using a combination of these two, we reached by the end of last summer a success rate of 93%. Meaning in 93% of all buildings, we were able to automatically find an admissible set of diameters for all of the pipes. Now, this seems to be quite a good value, but the problem is that the remaining 7%, that's where we find the most attractive buildings. So there we find the largest buildings, the most prestigious ones, and of course all the buildings which are very hard to plan. Last year, I gave a talk here at the M-Cubed on the classic machine learning part. And there, someone in the audience posed a question about dynamic programming, which is a precursor of reinforcement learning. And that kind of sparked the idea to use reinforcement learning to address these remaining 7%, to address these hard-to-plan buildings. In order to see how this works, we need a little bit of background on hydraulics. Nowadays, we find flat roofs almost everywhere. And to protect our infrastructure, we must be able to deal with the largest precipitations that can take place only once every 30 or 100 years. So on roofs like these, it rains up to 500 liters per second. That's about 200 bathtubs dumped every minute. So there's a lot of water coming down these roofs. But nonetheless, the water level must not rise above 10 centimeters. If the water level rises above, then the water gets too heavy on the roof and the roof collapses. So to steer these water masses safely and reliably off the roof, we need on one hand a carefully designed piping system and on the other hand a hydraulic trick. And this hydraulic trick is based on negative pressure. Using negative pressure, we can literally suction off the water off the roofs. Thus, the dangerous water masses cannot accumulate anymore in the first place. And it works like this. By choosing special pipe diameters, the pipes fill up fully during heavy rains. Thus, in the vertical, we get a closed water column, which results in a negative pressure, suctioning off the water like a vacuum cleaner. Also, thanks to the specially chosen diameters, we have high flow velocities inside the pipes. Thus, the pipes cannot clog anymore, and we essentially end up with a self-cleaning system. Moreover, conventional roof drainage systems, they have a slope, which is difficult to install and requires a lot of space. And of course, syphonic systems don't have this disadvantage, and there are, of course, many more advantages as well. If you're interested in the marketing part, let me know. I'll tell you as well. But let's make an example. This roof here, with its about 7,000 square meters, yields about 200 liters per second. So to find the right diameters for the piping system, we need a planning software, like the one developed by Geberit. So let's see how this works. So we have here a schematic graphic user interface, and these elements here represent the outlets. That's where the water enters the system. Then the waters flow through these lines. They represent the pipes, and the water leaves the system down here on the ground connection. When we start the calculation, then the algorithms first try to find suitable dimensions for each of the pipes, and afterwards a hydraulic simulation is performed. So let's do this. Thus, we get for each pipe, we get one line in this hydraulic list. And for example, here the algorithms failed and did not find a suitable set of diameters. Thus, here we see the red ones, these are errors. Here we see we don't reach a suitable flow rate, or here we have too low flow velocities. So in cases like this, I, as the end user, now must guess better diameters. And I have to do this either based on my experience, my hydraulic knowledge, my gut feeling, whatever. I have to choose it now. So it will be my fault. So for example, now I choose a larger diameter and I restart the simulation. Now maybe you noticed it improved a little bit here, but it was not good enough, so I try another pipe, for example this one here. We start again. So now this problem up here is solved, but some new problems surfaced down here. So this is really kind of a vicious circle. I need a lot of time, a lot of intuition, and often finding the solution for a building like this can take hours. And constructing a building or a piping system whose simulation shows errors is truly a bad idea. So let's assume that the simulation shows that we have too high a negative pressure in one of the pipes. Then under heavy rains, the pipes will be squeezed together. So this will look like a giant fist squeezing the pipe together, and the water will stay on the roof. Then the roof collapses, and in case the roof resists and does not collapse, then the water spills over the sides of the building and damages the facade. So this really, you don't want to do that. But for us now, we have enough hydraulic background to apply reinforcement learning to it. So to use reinforcement learning for our hydraulics problem, we must turn it into a game. Meaning we have to define a set of actions, we must define a game state and a reward function. And of course we also need a game engine. And the game engine contains all of the business logic. In our case, that's essentially the hydraulic simulation part, which is already built in ProPlanner. That's why we use ProPlanner as our gaming engine. So we now have to define a set of actions. In the case of the snake game, it was very easy to define the actions because these were simply the buttons that we had in our game. In our hydraulics case, we must be able to select one of the pipes in the hydraulic list. That's why we need a up and a down action to move up and down the hydraulic list. And we need an action to increase or decrease the diameters of the pipes. Thus, we initially started with this minimal set of actions, just these four. And it worked. But when we looked at how our users actually do the planning, then we noticed that they often jump directly to the next error and then fiddle around with the pipes in the neighborhood of this error. Or they often jump directly to the next vertical pipe, because vertical pipes have a strong impact on the overall hydraulics of the system. So for the fun of it, we also added these two convenience functions and then trained a new policy. And it turned out that using this seemingly convenience function actually improved the success rate of the policies quite a bit. So let's now define the game state. Now, in the case of the snake game, the game state is also obvious. It's simply the board, which we can either encode using a matrix or an image. In the hydraulics case, we notice that our users actually only take a look at the hydraulic list. So they don't care about the graphics representation anymore. They use it only to draw the system, but then they don't care about it anymore. So we simply used all values in the hydraulic lists as our game state. But we did not include the arrow coloring, so the red and yellow background. And that worked as well. But it turned out for our users, the arrow colorings are actually an important visual clue. And so we also tried to add these arrow colorings into our game state. And it turned out that also for the algorithms, these clues are quite important, because once more it increased the success rate of our policies quite a bit. In general, when you have designed your actions and your game state, it might be a good idea to test if you've chosen a suitable design. And you can test it by taking this game that you've defined and ask a human expert to play the game you've defined. So if a human user is able to play the game, just taking one of the actions you defined and just by looking at the game state that you're offering, and if the human user is aiming to play and win the game, then you might have a good starting point. So let's move on to the reward function. Actually, the reward function is quite subtle to design, because depending on its design, you might get quite surprising and unexpected policies out of the algorithms. As an example, let's assume that we didn't give any points for eating a fruit. So we only give a point for winning the snake game. Now, because the algorithms start with a random policy, that means it becomes quite unlikely to win the game, just by using this random policy initially. Now, this means that for the snake, life becomes quite miserable, because life now just consists of a sequence of painful steps and ends in death. It is very unlikely that it will ever have a positive experience. From this point of view, it suddenly becomes a very reasonable strategy for the snake to jump off the board as fast as it can, avoiding all the pain of life. In our hydraulics case, our goal was to reach a solution which has 0 errors. That's why we give 1 positive point for each error less and 1 negative point for each error more or in addition. And that works quite well. But initially we started with a slightly different reward function, namely one that gave a positive point for any reduction of errors, independent of the error count, and a -1 point for any increase in errors, also independent of the error count. Now that resulted also in a kind of funny policy, because now the policy started to reduce errors one by one, very carefully, taking each positive point for each error less. When it got close to 0 errors, it made one big mistake, paying for it with -1 points, generating many new errors, and then happily starting again to eating off one error after the other. Like this, it was able to reach arbitrarily high scores without ever solving the system. And of course, that's not what we wanted. So in general, it's also very tempting to put a lot of cleverness into this reward function. But often, the more cleverness you put into the reward function, the more surprises you get out of the policies. So it seems to be a good idea to start with as simple a reward function as you dare, but not simpler. So by now we've got almost all elements that we need for our reinforcement learning. The only remaining part is now the network architecture. And we tried a couple of different architectures. But in the end, it turned out that the most simple architecture, one using only one hidden layer, was actually roughly as good as all the other very cleverly designed architectures. So we went for the simple one. So let's see now how this looks like in ProPlan. So I fire up now the gaming engine. So of course, this is the gaming console. Of course, you won't see it in the production version. So I undo all the changes. And now, for example, I can use the down action to move down the hydraulic list. I can decrease a diameter. Of course, this changes the hydraulics, and therefore a new simulation is started. I can jump to the next error, or continuously jump to the following error. And then, for example, decrease the diameter again, and so on. Or jump to the next vertical pipe. But let me undo my gut feeling is not that well educated. So I undo all these changes. We roughly have an installed base of about 7,000 clients in about 42 countries all around the world. But only about a dozen of our users reach a success rate above 99%. So these are true world champions. And an average user, like one with 2 or 3 years experience, may easily need a couple of hours to find a solution for this building here. And novice users often don't find a solution at all. So let's see how our policy performs. So the computation now starts with our traditional heuristics, then goes on to the classic machine learning part, and you will see when it starts with the reinforcement learning part. So now it started. At the total reward, you see the number of errors it already reduced. So you see sometimes it makes mistakes and it adds new errors to it. That's very similar to how our users also work. And finally, the one. So, using the combination of the traditional heuristics and the classic machine learning, we reached this success rate of 93%. Adding reinforcement learning to it, we were now able to reduce our fail rate by more than 70%, resulting in an end-to-end success rate of now 98%, which is really a great relief, in particular for our novice users, because now they are able to reach a solution for many buildings which they before wouldn't have been a chance to find a solution for. So in this talk, I tried to convey you some intuition on how these reinforcement learning algorithms work. If you have a problem at hand and you want to use reinforcement learning, you must try to turn your problem into a game by defining a set of actions, a game state, and a reward function. Once you have that, then the algorithms will typically start with a random policy and try to continuously improve this random policy until it finds a reasonably well-trained strategy for the problem you're posing. One nice aspect of reinforcement learning is that it doesn't need a training data set, so you don't have all the work and labor associated with collecting data and combing and cleaning and doing all the statistic stuff around it. For us, it turned out that using reinforcement learning side by side with classic machine learning or supervised machine learning proved to be really very fruitful. And also, I think reinforcement learning is not a replacement for supervised learning or anything like that. It's more, it attacks or it addresses kind of a different set of problems, and you might have quite a few nice results out of it. So in case you are embarking on your own reinforcement learning adventure, please let me know. I'll be very interested in hearing what you're up to. Or later on, if you have questions, please get in touch with me. Write me a mail, give me a phone call, whatever. I'll be happy to hear what you're up to. And of course, if you have questions now as well. Thank you.